we are going to finish up the second part, or finish up the first part, I suppose, in the second part for polar coordinates and graphs. And there's not a whole lot to this, there's not a lot left, I suppose I should say, to this, but we just want to see, so we talked about how, if we're given a point that is, an XY point in the Cartesian coordinate system, or sometimes we call that a rectangular coordinate. There's a T in there. Rectangular coordinate. Then the corresponding, I'm having trouble spelling today. The corresponding polar coordinate is given by r theta. Oh my goodness. Polar coordinate. Where, right, we know a couple of things here. And so this is my polar coordinate, this is my rectangular coordinate, and these are just the points, right, in the XY plane, or now in the r theta plane. So when we look at graphs of functions, really a graph is just a collection of points, right? That's all a graph is. And so when we had this relationship to go from rectangular to polar or from polar to rectangular, we use the following relationships, right? We use the relationship that x squared plus y squared was r squared. So let me just refresh your memory here. This is xy as a rectangular coordinate, or as a polar coordinate. Whoa, settle down there, blue. We don't need to get crazy. Or we could think of that as r theta as a polar coordinate, right? And so what we found, where this is my r, this is my theta. And so we found these relationships between a rectangular coordinate and a polar coordinate. And that's what we're going to use when we are going to talk about graphs and equations, okay? So the relationships we found, x squared plus y squared was r squared, right? We also found that x is equal to r cosine theta, y is equal to r sine theta, and we used, a lot of times, I did, whether you did or not, I'm not sure, but I used the relationship between y and x to talk about tangent and to find my theta. So now let's talk about, how does this relate to, what are the graphs? I mean, aren't you excited to think about, I know you are, if I have an equation, what does that mean in polar coordinates? So we're going to look at is the relationship between polar equations and rectangular equations. And then we'll talk about the graphs, which are really just equations with y equal to it. So polar equations and rectangular equations. And basically, I'm just going to do some examples for you, using the fact that we know, right, we know this stuff. This stuff is going to be the key to switching from polar to rectangular or vice versa. So just a couple examples. Convert the following equations. Convert the following rectangular equations to polar equations. I'm just going to do some for you. And then we'll talk about what the graphs look like because they're so pretty. We can draw flowers. I'm very, very excited about that. I know that's silly, but sometimes in life, you just got to enjoy the simple things. So let's look at kind of a simple one. This is the most common one. But if I had x squared plus y squared, let's say equal 36. So we'll talk about the excuse me. We'll talk about the graph of this later. This is a circle, right? So we'll kind of circle back to this. Sometimes, you just crack yourself up and you have absolutely no reason. But what am I going to use to convert this to rectangular equations? So when you go to convert from polar to rectangular, rectangular to polar, vice versa, you really want to look at these relationships right here, and you want to see if there's anything that looks familiar, that looks like something you can use. And obviously in this case, I see that I have, ooh, look at that fancy color. I see that I have that x squared plus y squared, right? And what does x squared plus y squared equal? X squared plus y squared equals r squared. So that means that this whole thing right here, I love that, that's so cool, is r squared, right, equals 36. And then we can even go so far as to just say Well, that implies I'm going to take the square root of both sides. Normally when we bring in a square root, right, we have to worry about the plus or the minus. But because I don't have I have to worry about that because r is your distance from the pole or from the origin, it's always going to be positive. So we just say r is equal to 6. And we'll talk about later what the graph of that looks like, which you can probably just guess. So B, let's look at one other one. What if I had something just like, you know, something that's pretty simple, well, relatively simple, minus y equals 1. So something like this, there's not really a whole lot to do here. A lot of these, it's a little bit unsatisfying because there's not a whole lot to do. So, oh, I don't want that quite yet. We'll get to that in a moment. But what am I going to look for here? So I'm going to look for what I want my x and y's to go away basically, and I want everything to be in terms of r or theta. So this x right here and this y right here, right? I have a relationship for x and y right up here. So what can I do? I can just literally make a substitution. I know x is equal to r cosine theta, and I know that y is equal to r sine theta. So I replace the y, replace the x and the y. The 1 and the 3 are constants. They don't care what the variables are doing, right? And so, I mean, that's it. We could, you'll see in practice, we could factor out the r and just be left with r times 3 cosine theta minus sine theta equals 1, and that's about it. Now, we could solve for r. That is something that sometimes we will have to do, especially if we're graphing, like not in decimals or something, but in our, TI-84s. That's something we might have to do is solve for r. But in this case, that's about it. It's pretty straightforward, I think, to convert from rectangular to polar. Sometimes you can mess with it a little bit, but in general, that's going to be kind of most of what you do. Now, the other way, there are a few little tricks, okay, for certain ones. So let's look at an example of convert from polar to rectangular. So to convert to rectangular. And let me kind of show you this. Well, the first one here, this one shouldn't be too bad, but again, sometimes there are some tricks to it. So if we went, actually, let me start with something like this. So what if I had r sine of theta equals 4? So again, I'm going to come up, I'm going to look at the relationships that I have between these things that we're dealing with. I have an r sine theta. Well, what do I know r sine theta is equal to? That's equal to y. So if I rewrote this, this would just be y equals 4, which is pretty cool because what this says is that if I have r sine theta equals 4, really I just have a horizontal line, and we'll kind of see that that's true in a little bit. What if we had something like r equals 2? So if I look up at the relationship between my variables, my rectangular and my polar, notice I don't have just r by itself. I could solve for r, but then I would have to bring in a plus or a minus, right? And so what am I going to rewrite? Am I going to put a plus the square root of x squared plus y squared, or am I going to put a minus the square root of x squared plus, or x squared plus y squared? So the way that we can kind of get around this is I can take this equation and I can square both sides. And the reason I want to square both sides is I want to get an r squared. So what is it? I want to say it's cheating, but it's really not. So look at what I get. I get r squared equals 4. And then what do I know r squared is? R squared is x squared plus y squared. And now that just equals 4. So there's my rectangular equation for something that was a polar equation. And then I want to do one more because this one can be a little bit tricky. What about something like r equals 4 sine theta minus 5 cosine theta? All right, this one's going to be a little bit more tricky. But let's see what we have going on here. So again, I have just a plain r. That's not going to help me too much. And what are we missing here from this guy right here? Well, I know that x equals r cosine theta, right? And I know that y equals r sine theta. So what am I just missing here? I'm missing an r. If I had an r, right, I could solve. Remember, I want just x's and y's in this equation. I don't want to like solve for cosine and have an r there. So the trick is going to be to multiply everything by r. Whoa. So I'm going to multiply both sides of the equation by r. Now look at what that gives me over here. This is such a great trick. Well, I get r squared. If I take my r through here, I get 4r sine theta minus 5r cosine theta. And now we're raring to go, right? Look at what I have. I have my r sine theta. I have my r cosine theta. I even have an r squared, which is easier for me to work with than just a plain r. So what does r squared become? That becomes x squared plus y squared. What does this r sine theta become? It becomes 4y. The r cosine theta becomes just x, and then I could put everything equal to 0 if I wanted to, you know, or whatever. I could rewrite this as x squared plus 5x plus y squared minus 4y equals 0, something like that. Okay, and this would actually be, I believe it's a circle if we complete the square and, you know, combine like terms. It's a circle that's been shifted around a bit, right? It's not a nice circle. Well, who's to say what circle is nice and what isn't? But I hope that makes sense. That's the big one, like that you want to, is multiplying by that r. That's the one thing that really kind of can be a little bit tricky, but I hope that kind of makes sense. All right, let's talk about these graphs and then we'll be done. So the graphing, I'm not going to have you graph these by hand. I don't really see a reason for it when we have our graphing calculator and we have Desmos, but I want to show you these because they're just so cool. That is basically the reason why I want to show you. So graphing polar equations. And let's talk about what we think maybe it's going to look like, because I know you want to do that as well. Polar equations. So a couple things. Let's look at just some of what this might look like if we're given a polar equation, and then we'll just kind of describe it and we'll call it good. So something like r equals 6. Right? That was that one that we had before. And what did we see before? R equals 6. What is the Cartesian or the rectangular equation for that? That's x squared plus y squared equals 36, which we know. Whoa, sorry. My book just about fell off the desk. We know that x squared plus y squared equals 36 is a circle of radius 6 centered at the origin. But let's also think about, so this is a circle, right? Centered at the origin. 0, 0 with radius 6. That's the description of this. And why does that make sense, though, in terms of, oh, guys, look at this. This is just amazing. Look at that. Yes. Isn't that cool? Whoa, not quite getting there yet. I know you miss my trying to draw straight lines, but the problem is I don't have a circle one for it, but close enough. So let's think about why it makes sense. 5, 6. 1, 2, 3, 4, 5, 6. Close enough. Why it makes sense. Apparently I can't do that all at the same time. For this to be a circle. Well, remember r equals 6. So any point on my polar graph, right, is going to be r theta. So notice any point now, if r is 6, is going to be 6, and then theta can be basically whatever it wants. So when theta is 0, I'm at 6. When theta is pi over 2, I'm at 6. When theta is pi, I'm at 6. When theta is 3 pi over 2, I'm at 6, right? When we're at pi over 4, I'm at 6. So what's going to happen here? Sorry, I can't start over there if I'm going to try and draw a circle. Oh, man. Oh, that's just so sad. Oh, that's just the worst circle in the whole world. I'm sorry. I hope yours are better in your notes. It's just a circle of 6 because my theta can be whatever it wants, right? So at pi over 4, I would be 6 away. At pi over 6, I'd be 6 away. At pi over 3, I'd be 6 away. So you can see that I get a circle of radius 6. I can't handle looking at that anymore, people. I have to get rid of that. That's really, really, really bad. But there's some other really cool ones, and I'm actually just going to kind of show you these on Desmos right now, and then I'll show you how to do them on what am I trying to say, people? On your calculator. So let's look at something like r equals 1 plus cosine of theta. So I am in I'm in Desmos, okay? I'm just going to graph something like this. This is called a cardioid. Or cardioid, and it's kind of cool. Whoops, let me try and make that so you can actually see it. There we go. And again, this is 1 plus cosine of theta. Move this over so you can see which one's what I'm doing here. And this is called a cardioid. If I did 1 plus cosine of theta, oh, that one's cool. If I did 1 plus sine theta, you see I get a cardioid kind of in the opposite direction. If you think about what's happening here, like let's think about what happens if theta is 0. If theta is 0, then sine of 0 is 0, so I would get r equals 1. So notice at 0 degrees right here, which would be on the x-axis, my r is 1. When theta is pi over 2, right, I get sine of pi over 2 is 1. 1 plus 1 is 2. So at pi over 2, I should be up at 2. At pi, I should be back at 1, negative 1 now, right? Because I have not 1. R is 1. You got to think about that. So my angle is pi, but my distance is 1. Why do we come down to 0 right here? Well, if you put in 3 pi over 2, the sine of 3 pi over 2 is negative 1. 1 plus negative 1 is 0. So I'm going to be 0 away from the center. Okay. One I wanted to show you really quick. Look at this one. No, r equals 1. That's r equals 1 is a circle of radius 1, right? Of course. But let's look at, I'm going to draw some. Well, first of all, also, what do you notice about cosine? It's along the x-axis. That's kind of what the cardioid is. The sine was around the y. Well, that would make sense because sine are my y values, right? And cosine are my x values. But these are the ones that are really fun, like cosine of theta. Not of theta, 3 theta. Oh, look at that. So you can mess around with these. I'm not going to make you actually graph these by hand, but I do want to show you how to graph these on your calculator because calculators takes a little bit to figure out. But you can make really cool shapes. 3 theta will give me a flower with 3 petals. If we did 6 theta, I get a flower with even more than that, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, twice that. 6 theta, 8 theta. You can make some really pretty things. If we did sine, right, that's just going to determine where sine of 3 theta. Notice it's just shifted a little bit to be along the y-axis. So polar coordinates, you will investigate polar coordinates more when you get to Calc 3. If you stay with us at Western, that's when we really delve deep into polar coordinates. But they're just a good time. You just can make some really pretty pictures with them. One that is a little surprising, but do you remember we had y equals 4 when we had r sine theta equals 4, right? Notice this is just a horizontal line at 4, which is what we expect it to be because this is y. Another way that we can write that if we solved for r here is a lot of times you'll see that written as 4 cosecant of theta. And it's the same thing because it's just dividing by sine, all right? So what happens, you just get these angles that keep going out, and because you have 1 over these fractions, it gives you really big numbers, so your arc gets really, really, really big because you're dividing by some small numbers. Results in a really, really big number, okay? All right, let's talk about how to do this now on... Whoa, hold on, people. Let's talk about how to do this on your calculator. Okay, so I haven't done anything to my calculator. It's T84. I know it's old school. I realize you guys have fancier calculators with colors and stuff, but we'll just do this on the 84. So the first thing you want to do is you want to go to mode. And when you're in mode, you want to make sure, first of all, that you're in radians. Okay, so go to radians, and then we want polar coordinates. So go to polar coordinates. There are all these different things like parametric that you'll talk about in Calc 3 and different types. So I'm going to go to polar. I'm going to go ahead and quit out of there, and I'm going to go to y equals. And I already have something like 2 plus cosine of theta. Okay, so that's going to give me a cardioid. So let's go ahead and put in 2 cosine of theta. And then the important thing about this is when you go to window. So if you graph this and you don't see... So if I graph this, I don't quite see everything I expect I should see, right? I expect that I should see, well, let's just go back to what we had before in Desmos. Oh, it's still thinking. And do 1 plus cosine theta. We expect to see a cardioid, right? But we don't quite see that. So first of all, a couple ways that we can switch this after it gets done thinking. Let's go to our window. So here's what your window is. So what this window is going to give you is this number right here is going to be the smallest value of theta you're going to get, and then the biggest. So I'm going to go ahead and set theta equal to 0, and then I'm going to go around theta. that looks like, you know, about 6 pi times. So you can actually put that in. How many times do you want to go around? If we want to go around 3 times, we could do that. So we could do 6 pi, or we could even just go around once. So we could do 2 pi. But sometimes you want to go more than that, especially if that theta is going to be changing the period of your function at all. And then why you see this number right here, what this theta step does, if you're not seeing the whole graph, that's what you want to change. You want to change that theta step, because this is how many times it's going to evaluate a theta. Like if I just did pi divided by 2, okay, and then let's do x min to -5, x max 5, -1 for x min, 1 for maximum, get a smaller window here. Oh, sorry, I meant -5. And let's graph this right here. Now, the problem with this is I asked it to graph to find my values only every pi over 2. So it's finding at 0, pi over 2, 3 pi over 2, or excuse me, pi and 3 pi over 2. And it's plugging in those points, and then it's just connecting the dots of only those 4 points. So when I go to window, I need to make that smaller. What if I did every, now I don't want to freak my calculator out, but let's do every pi over 10. And then I think we can go -2 to 2, -2 to 2. And we'll do pi over 10. That should give us a nice curve. Yeah, that's pretty good. So what that's doing is it's taking your first angle right at 0, then it's doing pi over 10, right? 2 pi over 10, 3 pi over 10, 4 pi over 10. And those are pretty small, small little chunks of it. Or if we wanted to do something a little bit more fun, like 2, I know, that is fun. I know it's fun. 2 sine of, let's do 5 theta. Oh, and the theta, let me tell you where to get that theta. So the theta, you're just going to use that variable key, the xt theta n, that's your variable key. So I want a 5 theta. I'm going to graph and see where I'm at. That's horrible. So let's set my window a little bit different. So let's go ahead and go from -6 pi to 6 pi. And let's do pi divided by 12. And let's do, what was my function? So I have 2, right? So let's do a window here of maybe a -5 to 5, -5 to 5. And let's see what happens. That's a little bit better. I'm going to go back. Oh, so see how it's thinking? It's because let's go back to let's do 3. And let's graph a little bit. Still not great. We didn't get as nice as Desmos, and that's because my window again, I'm going to go back from 0 to 6 pi, and let's do pi divided by 24 and just see what's going to happen there. There we go. Now it's a little nicer, right? So I get a little bit, it's more curvy. That's kind of a math term. I could even do, I don't know, should we try it, guys? Pi divided by 48. Yeah, that's even better. And it's still going, right? Because I said 6 pi. We probably didn't need 6 pi. My period, remember, is 2 pi divided by whatever that was, 5. So I know I don't need to go to 6 pi. But it gives me an idea of what the graph should look like. I highly recommend Desmos for this. Or if you have one of those fancy calculators that has colors, that is pretty great to use as well. All right, guys, that's that. Again, on those ones where I asked for graphing, you're welcome to use your calculator. Use Desmos. I believe it's multiple choice. Remember, though, on the test, stuff will not be multiple choice. I'm not going to have you graph these on the test, but I put a couple in the homework just for fun. Let me know if you have any questions.